Hello everyone, my name is Connor Smiley, and in this video I'll be summarizing what deferred rendering is and my implementation of deferred rendering, which is what you're currently looking at. Simply put, deferred rendering is a lighting optimization in which lighting calculations occur only when a fragment is considerably influenced by light. In naive forward rendering, lighting calculations are applied to all fragments regardless of the influence of surrounding lights. Deferred rendering avoids this overhead by rendering light volumes in order to sample from textures containing the scene's position, normal, albedo, and specular information. Deferred rendering is composed of two render passes. The first pass is called the geometry pass, and the second pass is called the lighting pass. The vertex shader of the geometry pass is often identical to that of a naive forward renderer's vertex shader. It simply outputs the position, texture coordinates, and normals of each primitive to the corresponding fragment shader. So right here is our vertex shader output, and here are the calculations. Everything looks pretty normals. The commented code serves as a visualization aid, which we'll take a look at in a moment. But right now let's examine the fragment shader, in which instead of performing lighting calculations immediately, we simply output the three textures as mentioned earlier. Before explaining the lighting pass in greater detail, I've came up with a visualization aid to help us understand the data being stored in the textures, which we'll be sampling in the lighting pass. What we're looking at right now is normal information. Things are, for a lack of better word, incredibly normal. Although when it comes to rendering this display, rather than using typical normal information within the range -1 to +1, I've had to transform the data to color space, which is the range 0 through 1, in order to get correct visuals. However, when it comes to positions in view space, a bit more effort is required. Right now, the range is far greater than that of color space. So when we look at the top left quadrant, everything with a positive y value but negative x value will be green. Everything with both a positive x and y value will be yellow, and everything with a negative y value yet positive x value is red, and of course in the bottom left, everything has a negative value. So what can we do to correct this to get better information? Jumping back to our vertex shader, if we uncomment the code I glossed over earlier, we can output a corrected color value for visualization. The way we obtain this value is multiplying by the projection matrix in addition to the model view matrix, allowing us to transpose our coordinates from view space to eventually color space by first performing the perspective divide and then doing the same math we applied to our normals to transform from normalized device coordinates to color space. So with this correction, if we jump back to our fragment shader and also uncomment the input, change up our color assignment, we'll see much more intuitive position information, which is right here. So now you can see a smooth gradient that lines up much more intuitively with position information relative to the camera, just rendered in the correct color space. We won't be feeding this data to our lighting pass because we require the data to be in view space, but this just goes to show that we're not feeding one of 4 values to our lighting pass. We're feeding proper values. Lastly, if we take a look at our albedo specular information buffer, you'll notice that things are incredibly lackluster because I wanted this scene to be more cartoonish rather than photorealistic, and also because I am not an artist in the slightest, so I filled it with white, but if you wanted a more realistic scene, here's where you'd be adding that information. So, tying this all together, let's dive into the lighting pass. We start off by rendering a full screen quad, or a full screen triangle if you're really edgy, and then moving on to the volumetric lighting shader. So instead of computing our lighting information like normal, where we perform calculations directly as seen in forward rendering, we instead sample from the screen space coordinates of our lighting volumes. Here's what that looks like. So If you look very carefully, you'll notice that all of these little circles correspond to the areas of influence of light in the main scene, when I alternate. So now they're in the middle, and they're slowly moving out to the outside. So that results in only lighting the appropriate fragments rather than trying to compute each light's influence on every single fragment of each of these wonderful skyscrapers. So that pretty much does it for my demonstration. However, there's a couple more things I'd like to go over. My demonstration implemented a little bit of customization. So if we stop the camera real quick and we do this, we can control every single light individually. Now, in order to implement such granular control, I made a few performance compromises. When examining the volumetric lighting shader, you'll notice that there's only one light worth of information. But this doesn't make any sense because my scene is rendering 25 lights to start. The reason why I did this was really just laziness because I wanted a dynamic amount of lights. But the cost is that every time we want to render an additional light, we have to rerun the entire screen quad, which is very, very suboptimal. So if I instead was happy with a static amount of lights, I could send up an array of lights, and that would alleviate a lot of draw calls and needless texture sampling. So that definitely would have been a substantial improvement going forward. Another thing to note about deferred rendering is it's not a be-all, end-all solution. When it comes to transparency, you lose your information, so there's various workarounds such as depth peeling and a lot of other stuff that's best touched on another day. And the other thing is deferred rendering is very bandwidth bound since you're writing to 3 textures or even more if you need some auxiliary information in your geometry pass. And you're also, resolution limited when it comes to the lighting pass when you're texture sampling. For example, if your buffers are 4K, that's going to be a lot more costly than if your resolution is something like 640 for 480. As an aside, here's a look at my dynamic light system. So every time I press the light key, we spawn a brand new light within our scene. Sometimes they're a little hard to see because they're off screen due to the sinusoidal locomotion. And another thing I feel really silly about is I could still use a fixed size array to render all my lights. I would just have some sort of cutoff index based on the actual number of lights in the scene. So that would be something to remember for next time. And if I keep spamming the light button, you can even notice that my frame rate sort of slowly starts to take just because the absurd amount of texture sampling taking place for additional lights. So this was an awesome learning experience. That concludes my demonstration. Deferred rendering, very fun algorithm, lets you see a lot of beautiful colors and achieve a lot of things you can't in naive forward rendering. Thank you very much.